This video is for section 10.3. So the first activity, you were supposed to find out how arc measures and chord measures were related, and hopefully you found that when you have a pair of congruent chords inside a circle or inside congruent circles, that the arcs that make them are congruent, and vice versa. If you have a pair of arcs made by chords in the same circle or congruent circles that are congruent, then the chords will also be congruent. So that's what this theorem is saying. FG and JH, if they are congruent, then the arcs FG and JH are also congruent. And vice versa, if the arcs FG and JH are congruent, then those chords made by segments FG and JH are congruent to each other. So in this problem, we can see that arc MN and PQ are marked congruent, which means segment MN and segment PQ are also congruent. So that means that 2x plus 1 has to be equal to 3x minus 7. So x is equal to 8. And so then MN and PQ are both equal to 17 when you plug 8 back in. In the next activity, you were supposed to use this picture, recreate this picture, and make a line that goes through the center of the circle that is perpendicular to this chord. Hopefully you found that when you did that, the chord was bisected. So that's one part of this theorem that you should know, that a line that goes through the center of the circle, this is circle A, that is perpendicular to a chord bisects that chord. Also, if you make this line so that it bisects the chord, you'll find that it is perpendicular to the chord. And if you have a perpendicular bisector to a chord in a circle, it will go through the center of the circle. So here are the three things that you should have gotten out of that activity. A diameter, a radius, or any line or segment that goes through the center of the circle and is perpendicular to a chord bisects a chord, also bisects this arc here. Any perpendicular bisector of a chord, so in this case AB is bisecting XY and is perpendicular to chord XY. So any line that or segment that is perpendicular and bisects a chord will go through the center of the circle. And if a line or segment goes through the center of the circle and bisects a chord, then we know that it is perpendicular to a chord, and you can make a right angle at that intersection. So here, we know that circle O has a radius of 13 inches. Now OB is a radius. In problems like this that you work in your classwork, OC will not be drawn in here. That will be something that you need to do. And you need to recognize that OC is a radius and is also the hypotenuse of triangle OXC. And right here, triangle OXC is a right triangle. We know this because they tell us that radius OB is perpendicular to chord CD. And so all four of these are right angles. Also, we know because radius OB is perpendicular to chord CD, from the theorem we just learned, we know it bisects chord CD. So we know CX and XD are congruent. And we know it bisects these arcs, so arc CB and arc BD are congruent to each other. So we're going to use that for this first one. If CD is 134 degrees, CB is also is going to be half of that, because CD would be this whole arc right here, and CB is going to be half of that, since this radius is cutting that arc in half. So then that would be 67 degrees. Now to find OX, we're going to have to use this right triangle right here. Because OC is a radius, we know that that is 13. They tell us that arc CD is 24 inches long, so we know each of these is 12. And by using the Pythagorean theorem for this right triangle here, we can find OX. So if we do A squared, 12 squared, plus B squared equals C squared, since OC is the hypotenuse, we get B, which is OX, equals 5. In the last activity, you were supposed to use the GSP file that I had on Google Classroom, and hopefully you found that when these chords are the same distance or equidistant from the center, so we can see here that chord WY and chord VT are both 3.72 centimeters from the center, that they are congruent. And this also works backwards. If you have a pair of congruent chords in a circle, they will be the same distance from the center. And when you move this around, that stays that same. Chords that are equidistant from the center are congruent, and congruent chords in a circle are equidistant from the center. So that's what this theorem here is saying. So when they tell us that A, C, and DF are equidistant from the center, right away we can conclude that chords DF and AC are congruent to each other. Once again, these lines here won't be drawn in for you, these segments, but recognize that AG and GF are radii. And so we're trying to find AC. We know that these segments right here, these distances from the center, because they're distances, they have to be perpendicular. So there's a right angle here and here. Because these are segments that are going through the center of the circle and are perpendicular to the chords, they're cutting these chords into two congruent parts. And same with these. And we know AC and FD are congruent, so all of those parts are congruent to each other. And finally, we know that these each are radii, and so are 26. And so again, we can use the Pythagorean theorem with these right triangles, and we can say that 10 squared plus B squared equals 26. So we get B squared equals 576 when we square these out and subtract. And so B equals 24. So 24 is going to be these lengths here. And finally, AC is going to be those added together, or 48. And DE is going to be just one of those parts, so that's going to be 24.